Today we'll be looking at how to figure out electron configurations. We know that Schrodinger's equation shows that there's 7 energy levels. Each one of those levels has progressively more shapes for the electrons to travel in as they go around the nucleus. And the way you fill those up is progressively from the 1s orbitals on up, depending on how many electrons you actually need. Now this energy level diagram is one way of writing out the electron configurations. And let me show you how this works. Let's say, for example, we wanted to consider, well, let's say hydrogen from the periodic table. Hydrogen has 1 electron. So we would say that hydrogen, I'm going to put a little 1 there for the 1 electron, and we'll start at the bottom with the 1s orbital. Now each one of these circles represents a place that the electrons can be, and there can be 2 electrons in each circle. So I'll say that if we start here, in the first energy level, the S shape, which happens to be a sphere, for hydrogen there's 1 electron. So first energy level, S shape holds 1 electron. So hydrogen, we say is a 1s1. Now what this really means is that if you have the nucleus of the atom there, and in the S shape, which is the sphere shape, there's 1 electron. So when I say 1s1, I mean first energy level, S shape has 1 electron. So let's say we were talking about helium. Helium has 2 electrons. So we would say first energy level, S shape, can hold 2 electrons. So instead of this being hydrogen, if we put another electron in there, that's like helium. But let's say we're doing carbon. Carbon has 6 electrons. So we'll start at the bottom and work our way up. Remember, each circle can only hold 2 electrons. So we'll say that carbon has, in the first energy level, it'll have 2 electrons. Now that's full, we'll keep going up, and we run into the 2s level. The second energy level also has the sphere shape. It's 1 circle, so it can hold 2 electrons. And then we run into the p's. Now there's 3 circles there for that. That means the 2p shape can hold a total of 6 electrons. Well, we only need 2 more, so we'll say 2p2. So that means that carbon has 2 electrons in the first energy level in the S shape, 2 electrons in the second energy level in the S shape, and 2 electrons in the second energy level in the P shape. What that really looks like is if this is the nucleus, there's the first energy level. It can hold 2 in its S shape. Here's the second energy level. It can hold 2 electrons in the S shape. Then the P orbitals have a strange shape. They're the dumbbell ones. That's one of the circles worth. 2 electrons can go there. There's another, and then this one is going in and out of the page. So there's 2 electrons in the P shapes. So when I draw this is a better, not great, but a better representation of where the electrons are. That's really meaning this. Now what if we had a really big one? Let's say we had, I'm going to look on the periodic table, let's say we wanted to do tin. Sn has 50 electrons. So we'll say, okay, I'm going to write it over here. Tin has 50 electrons. So if we start out at the bottom, we've got 1s2, and then we keep going up, 2s2, and 2p6. We keep going up, 3s2, 3p6, and we keep going up, and then something odd happens. There's an overlap. Instead of going to 3ds, we do the 4s's. Schrodinger had to write letters of apology for this, but it ends up being completely true, so we just keep going with this, and lots of experiments have shown it to be right. So after 3p6, we get the 4s2. Then, if we keep going up here, we run into the 3d10. And at this point, you're saying, okay, how are we doing? Let's count. If we look at these three, we've got 2 plus 2 plus 6 is 10. If we look at these three, we've got 2 plus 2 plus 6 is 10. And of course 3d10 is 10. So we've taken care of 30 electrons. Now we've got 20 more to go. So after 3d10, we've got the 4p6. And after 4p6, we have 5s2, which means we have 38 done so far. After 5s2, we have 4d10. So that means we've done 48. We just need 2 more, and those are in the 5p. So we say 5p2. So the electron configuration of tin looks like this. And if we were to try to draw it as a flower like that, it'd get really messy. The D's are very difficult to draw. But that's how you use the circle diagram to figure out the electron configurations. There is another way, and it has to do with the color-coded periodic table. The color-coded periodic table is set up to show the overlaps that came out of the Schrodinger's equation. And it's an odd system, but it works very well. So let's say, for example, we wanted to do carbon. You find carbon on the list, and you say, okay, carbon is going to be the goal. And then we read the periodic table from left to right, just like you're reading a book, and you start up at the very top. Now, the way the colors are set up, the red in mine is energy level 1, orange is 2, yellow is 3. You may have made a chart with different colors, and that's okay. But it's also set up to show the different blocks of the periodic table. It's actually quite amazing. The S levels can hold 2 electrons. We know that, the S sphere shell, and there's 2 electrons across in this particular column. So this is called the S block. Now the p orbitals can hold a total of 6, and there's 6 across in this block over here on the periodic table. It just so happens that boron ends in p1. Aluminum ends in something p1. Germanium ends in something p2. So it works perfectly. Back to the S block, magnesium ends in something S2. Rubidium ends in something S1. Now it also works out that the d orbitals can hold 10, and the transition metals are 10 across. And scandium ends in something D1, zirconium ends in something D2. The same pattern works for the lanthanides and actinides, the rare earth metals. There's 14 across here. The F block can hold 14. So lanthanum itself ends in something F1. Praseodymium ends in something F1, 2, 3, something F3. Very nice setup. So let's say we're doing carbon. You find carbon there, and you start at the top and you read your way along until you get there. It takes about 3 examples to watch until you actually get it. So I'm going to say carbon starts up here, and by the way, helium is definitely a noble gas, so it belongs there. But as far as the color-coded chart, it really should be here, because helium is 1s2. So helium's kind of an oddball. We just sort of let it be that way. But we start out with up here, and we say, okay, 1s2. And then we go down to the next line, and the color says 2. It's the S block, and there's 2 across, so I'll say 2s2. And then I work straight across like I'm reading it, and I run into the P block. The color still says 2, so it's 2p, but carbon is the second one in, so I'm going to say 2p12. All right, let me do another one. Let's do iron. So iron, we've got it right there. Once again, we start at the top, and we say 1s2. So we've read across that way, and then we go 2s2. Keep going across 2p6, because we need all of them. We haven't gotten to iron yet. Now notice I'm not counting electrons at all. That's the beauty of this. So I've done 2p6, go down to the next one, it's 3s2. Because the color says 3, it's the S block, and there's 2 across. So now we keep going. We haven't gotten down to the other yellow one, but we end up with the P, and there's 6 across for the next one. Okay, we're almost to iron. We haven't quite gotten there yet. Go down to the next one. The color says 4. It's the S block, and there's 2 across, so 4s2. And then we run into, finally, the 3Ds. Now, iron's in this one. So iron is 1, 2, 3, 4, 5, 6. Iron is 3D6. If you add all of these up, 2 plus 2 plus 6 plus 2 plus 6 plus 2 plus 6, you'll end up with 26. But I didn't have to do any counting along the way. All right, let's do another one. Let's say we want to do terbium. Let's get to a bigger one. So TB. Terbium, you start at the very top again, and you say, okay, we're starting at the top, 1s2, and then 2s2. Keep going across, we run into these guys, and that's 2p6. After these guys we go down, it's 3s2. After 3s2 we keep going across. The color is still 3, but it's the p's, so 3p6. I'm going to stop for a second. I made a mistake on iron. Can you change that to 3p6, please? Okay, back down to terbium. So 3p6. And then down here, 4s2. And after 4s2, we run into the Ds. So 3d10. Going across. Remember, we're aiming for terbium, which is down here, so we haven't gotten there yet. So after 3d10, we have the color is 4p6. After 4p6, we go down here. Color is 5, so 5s2. After 5s2, we run into this one, so that's 4d10. After 4d10, we run into this color is 5p6. After 5p6, we run into the next color is blue, so that's 6s2. And now we're in, finally, the F blocks. And terbium's in the middle of this one, so we're going to say the color is 4. It's the F block, and it's 1, 2, 3, 4, 5, 6, 7, 8, 9. 4F9. Once again, if you add up all the what look like exponents but really mean electrons, you add them all up, it'll add up to 65. So that's using the color-coded chart to figure out electron configurations. Next, we need to take a look at the noble gas shortcut. Now, I have no idea who actually invented the noble gas shortcut, but I can imagine it happening like this. Let's say you're doing a worksheet and you have to do argon. So you say, okay, argon is there. We'll start at the top, 1s2, and then 2s2, 2p6. After 2p6, you go down here, it's 3s2. After 3s2, it's 3p6. And argon's there. It's the sixth one over in the 3p's. So I say, okay, that's argon. And then let's say on your worksheet, the next one is calcium. So you find calcium, it's right there. So you start at the top again, 1s2, and then 2s2, 2p6. And you're starting to say, you know, they're kind of always the same. After 2p6, you go down here, it's 3s2. After 3s2, it's 3p6. And after 3p6, you go down here and it's 4. The color is 4, it's s2. Now, I can imagine that somebody looked at these two and said, oh my gosh, these are identical on the inside. The only difference with calcium is that it's argon with a 4s2 on the outside. Please, can't we do a shortcut for this? And some committee decided, yes, you can. And it's called the noble gas shortcut. So here's the rule. If you're talking about calcium, you can use the nearest noble gas that's smaller and put that in square brackets. So I'm going to say calcium is just argon, and I'll put it in square brackets. And then everything after argon, 4s2. So the rule is it has to be a noble gas that's in there. There's good reasons for that. Noble gases are unreactive, and the reactivity of a chemical happens after with the electrons that are beyond the nearest smaller noble gas. and they're on the end of this chart, so it's easy to work with. So calcium would be argon in square brackets, and then 4s2. Let me do another example. Let's say that we want to do copper. So copper is right there. What you do is you want the nearest noble gas that's smaller. To find that, you go up one and all the way over. So for copper, the nearest noble gas that's smaller is argon, because we went up one and all the way there. Now it's as if we've done argon, and we just need to keep going until we get to copper. So we'll go over here. The next one down is 4s2. Sort of saw that with calcium. But then we keep going, and then we have, the color is 3. It's the D block, and it's 1, 2, 3, 4, 5, 6, 7, 8, 9. 3D9. So that's the noble gas shortcut for copper. Let's do a couple more. Let's say we wanted to do a big one. Let's say we wanted to do lanthanum, La. You say, oh my gosh, this is going to take so long, but not with the shortcut. So you find the nearest noble gas that's smaller, go up one, all the way over, and it's xenon. So to find the nearest noble gas that's smaller, you go up one and all the way over, so you write xenon, and now it's as if we've done everything up to xenon. So we go to, the color is 6, it's the S block, and there's 2 of them, so 6s2, and now we're to lanthanum. The color is 4, it's the F block, and it's the first one. So that's lanthanum. Let's do aluminum. Let's say you've got aluminum. Al is going to be, where you go up one, all the way over, it's neon, in square brackets. So we've done everything from neon. So we go to the next level down, it's, the color is 3, so 3s2. And then we keep going. Aluminum's the first one there, so it's, the color is still 3, but it's P1. Let's say you wanted to do, let's do antimony, Sb. So Sb is going to be, you go up and over, krypton is the nearest noble gas that's smaller, put that in square brackets. After krypton, we go down, the color is 5, so 5s2. After that we go across, we run into the D block, and the color is 4, D10. After 4D10 we run into the P block, and antimony's in there. The color is 5. It's the P block, and we say 1, 2, 3. It's the third one in. So 5P3. Let me do one more, and then hopefully you've got it. Let's say you wanted to do Einsteinium, Es. So you go up and over, and radon. I don't know if you can see that on the video, but it is radon. That's right there. So now we've done everything up to radon. So we go down here, we have 7s2, and then we run into, the color is 5, it's the F block, and Einsteinium's there, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 5F11. I'm going to do one more. If you've got it, you don't have to watch anymore. Let's do, how about if we do LV? Livermorium, one of the new ones that's on the periodic table. Now you might have an old periodic table that really calls this let's see, that's 6, UUH, I think, appropriate. So let's say we go up one and over, that's going to be radon. So after radon there's 7s2. After 7s2 it's the 5F14s. After the 5F14s there's the 6D10s. After the 6D10s we run into the 7P, and it's 1, 2, 3, 4, 7P4. So that's the noble gas shortcut. There is one more shortcut called the last place electron, and that's even quicker than any of these. So the last place electron is even shorter than the noble gas shortcut. It's not always appropriate. Sometimes you need all of the elements, all of the electrons within the noble gas shortcut, but sometimes this is useful as well. So let's say you're getting the last place electron of, let's say you want to do aluminum. Now aluminum is 1s2, 2s2, 2p6, 3s2, 3p6, no, 3p1. Sorry, 3p1. So the very last one, 3p1, is the last placed electron. It's just the last one in the whole series, and it's really easy to find. For example, let's say that you wanted to find scandium. The last place electron for scandium, well, the color says 3, it's the D block and it's the first one in. So 3d1 is the last place electron for scandium. What if we were looking at promethium, 61, so PM? You'd say, okay, the color says 4, it's the F block, so 4F, and it's 1, 2, 3, 4, 5. It's the fifth one in, so 4F, 5. Let's say you wanted to find the last place electron of UUS, 117. Well, the color is 7, so it's the 7th energy level. It's the P block, and it's 1, 2, 3, 4, the fifth one in. So the last place electron, again, is the quickest that it comes. It's not always used because it's not, there's things that you miss when you get that, but there's lots of times it comes in handy. Hope this has been helpful. Have a great day.